Welcome to the next video in a course in real analysis. We'll be talking about the solutions to the exercises that were in lesson 7, discussing theorems about the relationship between real numbers and natural numbers. So here we recall that the goal is to prove that between any two real numbers is a rational number. We had this hint about how to attempt proving this. And now we go ahead and start our proof by assuming that A is a strictly positive number, B is bigger than that. We know that if we take the number B minus A over 2, that is a positive number. And so that will be like epsilon in the theorem from before about always having a small enough subdivision. And what that theorem tells us is that for this epsilon, there must correspond some natural number, we'll call it m, such that 1 over m, which by the way is a positive number, is smaller than that epsilon. So we know that this m exists. Now, also, we know from the any distance by enough steps theorem that there is a natural number such that A is strictly smaller than this, 1 over m times n. So we know that this n exists. We would like to choose the least such n. So we form the set of all of them. And this is a subset of the natural numbers and therefore must have a least element. So we'll go ahead and call that least element capital N. Now, it follows immediately that this value, n over m, is strictly bigger than a. After all, it is the minimum of this set, so it is one of the elements in the set, and it has that defining property. So we know that a is strictly less than big N over m. Let's deal with one case that we'll want to get rid of for the rest of the proof. So let's just talk about what happens when that big N is equal to 1. Well, if it's equal to 1, then we're really just talking about 1 over m, which we already know is some quantity, by definition, that is smaller than b minus a over 2. So in that case, we have that 1 over m is smaller than that, and that it is easy to show, right? You could even, here, let's just do it real quick. So we know that b minus a over 2 is itself smaller than b minus a, and we know that that is smaller than b because a was assumed to be a positive number. So there we have it, it's smaller than b. Well, what that must mean then is that this is a rational number bigger than a, smaller than b, and therefore is a number that satisfies what we need to construct for this proof. So there we have it. In the case where n is equal to 1, the theorem is confirmed. But then we need to consider all other cases. And so for all other cases, n will not be equal to 1, but it is a natural number, so it's at least 2. And now, keep in mind, right, what we're up to at this point in the proof is we already have a rational number which is bigger than a. We want to show that this rational number is also simultaneously less than b, so that it's in the range between them, strictly inside. Well, to prove that it is smaller than b, that n over m is smaller than b, that's what we're trying to show right now. As soon as we do, we're done with the theorem. So let's assume for contradiction that it's not, right? So that b is less than or equal to big N over m. Well, then it would make sense that if I go down by 1, right, if I take that numerator and reduce it by 1, and this is, by the way, why we had to separately deal with the case for n equal to 1, is that if it were equal to 1 and I go down by 1, I would get 0. That's not a natural number. It's just kind of an awkward part of the proof. So we just wanted to sort of separately handle the case where n is equal to 1. But anyway, now we know that n minus 1 is also a natural number because n is at least 2. And then we get this smaller number But also through basically this proof right here, we see that it is bigger than b plus a over 2. And b plus a over 2, I mean, that's the average between a and b. And the average between a and b, since a is the smaller number, that's going to be bigger than a. Well, that's going to lead to a contradiction because, after all, we were supposed to have that this big N over M was the least choice of N, big N, such that this would come out bigger than A. So that's going to be the nature of the contradiction that we get. And so you can see the write-up here, but because we found a smaller value such that the N, integer over M, or natural number over M, is bigger than A, that's our contradiction. Okay. So now that we've reached a contradiction, we now know that this quantity, big N over M, is in fact strictly smaller than B. And that's exactly what we needed to construct. So the proof under the assumption that A is strictly positive is now complete. But we need to generalize to the remaining cases where A is non-positive. But if A is non-positive, then we know that there must exist a natural number such that negative A, well, okay, why am I talking about negative A? Well, if you subtract A to the other side, then you get that A is negative A is a non-negative number, right? Let me just go ahead and write that out. So we would have that negative A is non-negative, and therefore I can apply the any distance by enough steps theorem to tell me that there must exist a natural number bigger than negative A. Now, I'm just talking that through. I'm not writing out all the details of that argument, but I think you should be able to fill that in. Leave a question in the comments if you're not able to fill that part of the proof in, but at least, give it an attempt. But I promise you that there is this natural number which is bigger than negative A. Okay, now that we have this natural number, which we're calling P, then we can basically take everything and shift it to the right by P. So, here, even if A is non-positive, and we're still talking about A being less than B, and we still want a rational number in between A and B, but what we can do is we can just add P throughout, right? If we add P throughout, then we will get that A plus P is going to now be bigger than 0. And that's easy enough to see from what we've shown already, because after all, if you just take that inequality, add A to the other side, then you get exactly what we're claiming here. So we get that this A plus P is now a positive number. B plus P is going to be bigger than that, easy enough to show by compatibility. And now that we have that these two numbers are both greater than 0 strictly, we can use what we proved in the earlier part of this whole exercise, namely that there must exist a rational number Q, which is in between them. Now that we know that this rational number Q exists in between our two A plus P, B plus P, we can subtract P throughout. We get this, and it is easy enough to show that if you take a rational number minus a natural number, that you get a rational number, and we're done. Okay, for the next exercise, we're going to show that every real number is between some two consecutive integers. Again, we're going to do this where it is allowed to be inclusive on the left, but not on the right. Okay, as before, we take an arbitrary real number, assume that it is positive, and that will just be a temporary assumption that we will remove at the end, kind of like how we did in the previous theorem. So we know from any distance by enough steps that there exists a natural number bigger than r. Moreover, there is a least such element, which we will call n. I won't go back through all of the details of that because it's very similar to what we just did in the previous exercise. And let's just note that because it is the maximum such element, then r is strictly less than that big N. And moreover, what we now need to do is we need to demonstrate that r is greater than or equal to n minus 1. And that is very easy to handle because if that were not true, this is like a quick proof by contradiction, but if that were not true, if r were strictly smaller than n minus 1, because n is a natural number, and at least for a minute, let's assume that it is not 1, so it is at least 2, then n minus 1 must be a natural number, and then it's a smaller natural number than the choice of n was. But that's a contradiction because n was supposed to have been chosen as the smallest. So by that proof by contradiction, very quickly, we know that this cannot be true. We cannot have r strictly less than n minus 1, so we must have that r is at least n minus 1, and we get exactly the inequalities that we wanted to demonstrate. We should probably go ahead and discuss separately what happens if n is equal to 1. Well, if n is equal to 1, then we already have that r is less than 1, and we knew from assumption that r was strictly greater than 0, therefore it is also greater than or equal to 0, and the claim has thereby been proved separately for its own sort of especially trivial reasons when we assume that n is equal to 1. So we have the proof when n is 1. We also have the proof when it is not 1. So we're done. This concludes the proof under the assumption that r is strictly positive. If r is non-positive, we do a sort of jog around, kind of like what we did in the previous situation. So under this situation, we can find a value of p such that r plus p is strictly positive. I won't go again through the justification of that. But now we can apply exactly the same result as last time. Since r plus p is a strictly positive real number, then we can find these consecutive natural numbers n minus 1 and n such that it falls inside of the range here. If we take a right, we're going to subtract p throughout. Remember, p was a natural number, so what we're doing here is we're taking a natural number minus a natural number, so this has got to be an integer, right? So this is an integer, and this is an integer also. So now we have that r is located between these two consecutive integers, and the whole proof is now complete. And I'd like to end on an invitation to ask questions. If you found anything in this video or related sections of the textbook confusing, then please leave a question in the comments and I may address it there. Or if it is a substantial enough task, then I may make a video and include the video in the playlist.